This is a continuation of our discussion of elementary operations. In this video, we are going to discuss complement of set. First, we defined what we mean by relative complement. For any set A and B, the relative complement of A in B, denoted by this symbol, B except A, or in some literature, they call it B minus A. This is the set of all elements in B which is not in A. So again, this is the complement of A relative to B. So anything that is not in A but relative to B. So meaning all elements that are outside A but still inside the set B. So in symbol, we write that to be the set of all objects X such that X is in B and X is not in A. Or we can also write it this way. All element X in B such that X is not in A. So this is all the elements in B that are outside A. So that's why we call it a complement of A in B. Now, a special case of relative complement is the absolute complement. And this happens when the set A itself is a subset of B. So when A is a subset of B, we call B minus A the absolute complement of A in B. So it only means that A is within or inside the set B. To illustrate the difference between relative complement and absolute complement, in general, A and B can be any set. So A need not be inside B. So what does it mean to be the complement of A relative to B? So the complement of A relative to B will be anything that is outside A. So this is the exterior of A, but it must be within the boundary of B. So we don't just get anything outside A. We only get what is inside B as well. So this set here is outside A but are still inside set B. So this is the relative complement of A in B. Now what does it mean on the other hand if B is inside or completely inside A? This is actually the definition of complement that we use back in algebra or lower mathematics. So if A is inside B, then anything outside of A will be the complement of A. But again, we are inside the set B. So these elements here outside A, but inside the box B are the complements of A. So this is still B except A, but in our usual notation in algebra, usually we write this as A to the C, meaning complement. Or in some literature, they use prime, but here we will not use prime since prime in other language means derivative. So instead, we'll just use A complement or A to the C. Again, we are always taking the complement with respect to a bigger set. So this is complement in B. Although in this representation, B is not mentioned, it should be understood that we're talking of a set A which is inside a bigger set B. So we only do that representation if B is established. We can simply denote that as A to the C to mean the complement of A in B. Let's have some example. Let's look at the set again, ABC, where A is the set containing ABCD, B is the set containing BDFH, and C is the set containing CDEF. If you want, you can actually do a Venn diagram here to represent these three sets. So A, B, C, D are the elements of A, but we know that A has elements common with B. So looking at our sets, we can see that the letter D appears on all the three sets. So we write D inside the intersection of the three sets. So let's say this is A, this is B, and this is C. Now the intersection of A and B is B and D. So I already have D here, so I only need to write B here. And the other elements of A are A and C. So I write A here, but C is common with C, so I'm writing C here. The elements of B are B, D, F, H. So F is a common element with C, so I'm writing F here, H here. And then C, the only element not listed here is E, and it's not common to any of the other sets. So to imagine A, B, C, and D, this is the Venn diagram for our sets. So what is A except B? So anything that is inside B but outside A. So A except B. Anything in A outside B. Right? So the first set will be the collection, and then you will remove. So this is the first, the collection, and then B will be removed from this collection. So the elements of A are A, B, C, D, and then we're going to remove anything that is in B, which is exactly B and D. So we're going to get the elements A and C. Now observe that if we on the other hand get B except A, so we're going to get the elements of B, and then we're going to remove elements of A. So the elements of B are B, D, F, H, but the elements of A here are B and D as well. So we're going to remove them, and we'll be left with F and H. So this is F, H. So we can see clearly now that complement is not commutative. A except B is not the same as B except A. Similarly, if we want to get A except C, so from A, we remove anything common with C, so we're left with A and B. On the other hand, if we remove C and D from letter or from the set C, since they belong to A, so we're left with AF. EF rather. So we have EF. B except C. So this is our set B. We're going to remove the elements in C, so we're left with BH. On the other hand, C except B, we remove again the elements that are in B, so those are DF. And we're left with EC. At this point, it is a very good observation to note that what we are actually removing from the set is the intersection of those two sets. For example, if you want to get C except or minus B, so all you need to do is to get the intersection of C and B and then remove that intersection. Whatever left in C will be C except B. So now let's show some properties of the complement. If A and B are set, then the following holds. A except A is the empty set, meaning if you have a set A and then you remove everything that is in A, then you're left with nothing. So how do we show that mathematically? So again, by set equality, you just have to show that every element on the left is an element on the right. So for every X, what does it mean for X to be in A except A. By definition of the complement, this simply means that X is in the first set and X is not in the second set. But these are contradictory statements. X is in A and X is not in A. So they're contradicting each other. So that means, again, as I've said in the previous video, whenever you have contradicting property of X, then X must be in the empty set. Or the empty set has such property. So you have from the first set, X is in A except A, you end up with X is in the empty set. So we can easily say that the first set by set equality is equal to the empty set. And we are done. Again, do not forget to justify your statement. This is from the definition of complement. Sometimes I'll just write the slash symbol since that are symbol for complement. And this is the definition of empty set. Okay. Next property. A except empty set is A. Intuitively, that means from A, we're going to remove nothing. So we're left with the same set. By definition, again, if as our observation a while ago, whenever we have a set A and B, and you want to get A except B, what you're really doing, rather A except B, what you're really doing is you're just removing this part of A, right? So that means whatever is left will be a subset of that whole set. So this is a subset of A. And that is true for any set. Okay? I will leave this as an exercise. A except any set, so the complement of B in A is a subset of A. So meaning if you remove something from A, what's left is a subset of the original set. So clearly, if I want to remove something from A, so I don't know what will happen if I remove an empty set. But because of this property of the set complement, we already know for a fact that uh, empty set, or rather that A except empty set is a subset of A. Alright? Again, you have to show the definition or the exercise. So we're claiming that A except any set is a subset of A. In particular, by taking B as an empty set here, then A except empty set is a subset of A. So that's an exercise. From exercise rather. All right. So that means we are just left with showing the other inequality. So this is already done. So what we want to show now is that the other inequality is true, that A is a subset of A except empty set. So now we can use the usual method of showing subset. We show that an element from the left is an element from the right. So what does it mean for an object X to be in A? So there's nothing left for us to say, but using logic, we can say that X is in A and we can add any true statement. In particular, we want the statement X is not an empty set. So again, that's the rule in logic. That's the addition for and or conjunction rule. So we have a statement P and a statement Q. Therefore, we can have the conjunction P and Q. So if you have two true statements, then you can add those two statements using conjunction. So since X is always not in the empty set, this is always true. So we have this property in logic. But what does the second statement means? X is in A and not in the empty set. Well, that means that X is in by definition of the complement. It's in A except the empty set. So that's the definition of complement. Now, we start with this, we end up with this. So what do we conclude? This imply that the first set is a subset of the second set, which is what we want to show. So by two-set inclusion, therefore, the two are equal. And we are done. Okay, let's have another example. Empty set except A is empty. Of course, it's already empty to begin with. If you remove anything from it, which you can no longer remove anything, then you're still left with empty. So empty set except anything is empty. Again, from our exercise, and you really need to show this exercise, empty set except anything is a subset of the empty set, right? We are using this property. A set A except any set, you remove any set from A, the result is a subset of the original set. So the original set is empty. We're removing something from it. So whatever we remove, the resulting set is a subset of the original set. Okay? So again, this is from the exercise. Now, what does it mean for something to be a subset of the empty set? We've already established in our previous discussion that there is only one subset of the empty set, and it's the empty set. So therefore, we can conclude that this empty set actually, except A, is equal to the empty set since empty set is the only subset of empty set. Unique ang subset ng empty set. Isa lang yon. So, kung meron kang isang bagay na napakita mong subset siya ng empty set, then that particular set is an empty set. Okay? Because of the uniqueness of the empty set. Nag-iisa lang siya. Okay? Alright. Now, let's have another property. If you have B except A, then naging empty yung sagot. So that will only happen if and only if B is a subset of A. Okay? Let me repeat. Meron ka daw B, tapos kinomplement mo siya with A. So inalis mo lahat ng laman ni A. Then ang natira daw empty. So that means it cannot leave anything from A. So that means, or it cannot leave anything from B. Kasi empty daw eh. So for it to be empty, dapat lahat ng B maaalis. So dapat pala yung buong B nasa loob ni A. Para pag inalis mo yung A, kasamang maalis yung buong B. Kasi you want the result to be empty. Now, hindi pwedeng may konting part si B na wala kay A. Because if you remove A at may natirang part ni B, then hindi empty yung B. So, para ma-remove mo completely yung B, dapat yung buong B nasa loob ni A. Or that means B is a subset of A. Okay? So, that's what we want to show. That this is only true if and only B is a subset of A. So, what does it mean for B to be a subset of A? Doon tayo magsimula because it's something that is easier to show. So, by definition, B is a subset of A if for every X that you have in B, then that X is also in A. So, that's definition of subset. Now, in logic, we have equivalent statements or what we call tautological equivalence, right? Now, P implies Q has two equivalent. In logic, it has two equivalent statement. This is equivalent to either it's contrapositive. So, the contrapositive of this statement is not Q implies not P. So, again, that's from logic. Or another tautological equivalent is uh, not P or Q. Okay? So those are tautological equivalent statement. Tautological equivalent statement. So these three statements are actually, they mean the same thing. Okay. So how do we use this in our problem? So we have the statement X is in B implies X is in A. So we have P then Q. So I'm going to use the second tautological equivalence. So this is tautological equivalence. So this is also equivalent to not P. So X is not in B or X is in A. Okay? Now, another property in logic is De Morgan's law. So whenever you have something being negated or you have a statement not, usually that's De Morgan's. So either it's negation or De Morgan's. Since you are involved with operation or, then we are sure that these will be De Morgan's. To recall what's the De Morgan's theorem in logic. So if you are negating P and Q, that's the same as negate P or negate Q. There are two versions of De Morgan's. The other one is if you're negating or. So if you have P or Q, then that's the same as negate P and negate Q. So that's De Morgan. Okay? So do not forget our rule in logic, the rule of inference, the properties, the laws in logic, because all of them will be used in proving properties of set. Okay, so if you have a statement not in B or something, so that's equivalent or that's parallel to this statement here. So not in B or something. Okay, so it's an or statement. So by De Morgan, that can be equivalent to this statement on the left hand side. So it is not true that P and Q. So X negate P. So X is in B and X is negate A. So X is not in A. So that's De Morgan's in logic. But look at that statement inside the grouping symbol. That statement means that X is in B except A. Right? Or that means if I again put the negation inside, so that means X is not in B except A. So this is from the definition of complement, and this is the negation. Now, X is not in B except A. So X is not in B except A. Well, we say, remember we say that we started with the fact that X is in B, and then we end up with the fact that X is not in B. Right? We have this situation. We have B, and then we have A. So this is B, this is A. We started with this fact. So we have an X here. So X is in B. And then it ends up to saying that X is not in B except A. Right? So what does it mean for X not being in B except A? So that can only happen, right, if X is in the empty set. So anything X in B that are not in B except A can only happen if that X is in the empty set. Right? So, hindi pwede na yung X natin na kay B, tapos element siya ng B except A, na may laman yung B except A na yon. So, it can only happen if yung B except A na yon, walang laman. Right? It can only happen if B except A, walang laman. So we start with the fact that B is a subset of A, and this is equivalently saying that B except A is an empty set. So we are done. Okay, let's have some more property of the complement. A intersection B, intersection B, intersection A is empty. So let's draw again set A and B, so that we can imagine what we mean by those sets. So if this is A and this is B. So A except B. So anything in A that is not in B. So ito yan. This is A except B. B except A is anything in B that is not in A. So this is the other side. So that's B except A. So intuitively, we can see that indeed the intersection is empty. But of course, we still need to show it mathematically. So how do we show that this set is empty? So madali lang. Again, all you need to do is to show that any element from one set is in the other set. So for all object X, we have X is in A except B, B except A. So what does it mean for X to be in the intersection of A except B and B except A? So by definition of AND, so ito muna unahin natin. So X is in A except B and X is in B except A. So that's definition of intersection. Now we can apply the definition of complement here. So X is in A and X is not in B. And the other statement is also a complement. So that means we have X is in B and X is not in A. Again, that's definition of complement. Now, as a logical statement, we have P and Q quantity, R and S. So everything is in terms of the logical operator end. So we know that the logical operator end is both commutative and associative, meaning we can regroup them and then we can just commute them so that we can combine the statement involving A. So by regrouping and then commuting, so we can commute this here and then commute it here para magkatabi na sila with A. So that means X is in A and X is not in A. And we can do the same thing. So once you commute this 2, so you have X is in B, not in B, and X is in B. So that's combination of commutativity and associativity property in logic. Okay. But we can see from the statements we have X is in A and not in A. So that's only true if X is in the empty set. And you have X is in the empty set as well. So since you have the same statement by idempotent property of the logical operator, and we can simplify this as X is in empty set. Again, this is idempotent property. And so we were able to show that the first set is equal to the second set. So therefore, A intersection B, A except B, intersection B except A is indeed the empty set. Now, another variation using the same set of that is A intersection B except A is actually empty. You have the same set, the same but another variation. This is A, this is B. So A is the whole set here, and then B except A is the other side. So we just want to show that this is also an empty set. Again, intuitively, we can see that they share no element in common. Okay? So we're not considering the boundary as a common point. Ha? We're only considering the shape as a intuitive boundary. So, ang nasa loob lang yung kino-consider natin. So, although magkadikit sila, or they share the same boundary, in terms of set, wala silang common element. So we'll use the same technique to show the equality. We just have to get an element from one side and then show that it is also equal to the other side. Yan. Okay. So for every x in the left hand side, so A intersection B except A, what does it mean? By definition, well, that means that x is in A and x is in B except A. So that's definition of the intersection. Now applying the definition of the complement, so we have x is in A and the compound statement x is in B and x is not in A. Definition of complement. But again, our statement involves only the logical operator n. So by again regrouping and then commutativity first. So we can commute these two. And then when you commute that, you can regroup A with A. Yeah. So we can regroup the statement x is in A and x is not in A. And then we have n x is in B. So that's again associativity and commutativity property of the logical operator. But we have yet again another contradicting statement, x is in A and not in A. So that can only means that x is in the empty set and x is in B. So that's definition of the empty set. Now definition of intersection, since we have an end, so x is in empty set intersection B. But we have a property of the intersection. Remember, every time you intersect empty to any set, the result is empty set. So that's the property of empty set. So that means X is in the empty set. So again, property of intersect of the empty set with intersection. So yung property yon? Intersection of empty set with any set is empty. Pag union, A ang sagot. Yung dalawang property yan eh. If you still remember. Okay. So, we were able to show that the set B except A intersection with A is the same as the empty set. Now, all of these properties involve relative complement. In particular, we also have property specific to absolute complement. Okay. So, in absolute complement, we have this property. If U is a set such that A and B are subsets of U, we have the first property, U except the quantity U except A is in A. To illustrate that in Venn diagram, so you have set A inside a bigger set U. So let's say we have a set U. So what does this expression means? So you're taking the complement of A, right? So this is simply A complement. The set outside, this is A. So the set outside A. Now, if you get the complement of that, so what is the complement of the shaded region? Of course, the complement of the shaded region will be the unshaded region, which is A. So if you get the complement of this, you get A again. So that's what we mean by this property here. Okay? The complement of the complement is the set itself. Okay, so how do we show that? Again, we can use this symbol if it's clear to us that we're talking of just a big set U. Sometimes you call that U a universal set. A set that contains both set A and B. Okay? So this is equivalent to the statement A complement complement. That's the same as A. Let me reiterate in U. Only in set U. So let's prove that. So how do we prove it? Again, to prove equality, as always, you get an element of the first set and show that it is also an element of the second set or the set on the right hand side. So what does it mean that X is in this set? So by definition, so we're going to use the definition of the complement on the first complement. So X is in U and X is not in the set U except A. Now, we do not have a definition of X not in. Our definition is X in. So, we cannot use directly the definition of complement on the second part. So, how do we fix that? So, first, we need to remove the negation symbol. So, this is the same as saying that it is not true that X is in U except A. So, that's by negation. So now inside the statement, we can now use the definition of complement. So let me rewrite X is in U and so whatever inside, it is not true. So it is not true that X is in U and X is not in A. So again, that's definition of complement. So that's the only time you can use the definition. You have a definition for in the complement, but you do not have a definition for not in the complement. That's why we apply negation first. Okay, so let's continue. So what does it mean for this to be not true? By De Morgan's, so you have a not statement and then you have an and. So that's De Morgan. So that means X is in U and So X is not in U, negate that statement, and will become OR, and then negate X is not in A, so it will become X is in A. So that's De Morgan. Now that we have an AND and an OR statement, we can now use distributive law in logic. So what does distributive law means? We will going to distribute AND. So we have X is in U and X is not in U. Or we're going to distribute it to X is in A as well. So we have X is in U and X is in A. Distributive law. Now, as a statement, the first compound statement means that again, X is in the empty set. Or the second statement means X is in U intersection A. So the first one is the definition of empty set, and the second one is definition of intersection. So now this is OR, so that means that X is in empty set union. Now what is U intersection A? Remember, from our given, U is a universal set, meaning it contains A. So if A is inside U, then by the property of intersection, U intersection A is A, the smaller set, right? So U intersection A is A, that's definition of, or rather property of intersection. I forgot the number, pero kasama yun, let me write that. So if A, nakalimutan ko ano yung ano, if A is a subset of B, then A intersection B is a subset of B. No, it should be equal. Yan. And then, you have empty set, union A. So, you use the definition of union. And finally, empty set, union A. So, we've already used that property of the empty set. This is the same as A. So, that's property of empty set. And finally, since we were able to show that anything on this first set here is also in this second set here, then they are equal. So U except the quantity U except A is A. Again, in language that the U is established, this is the same as A complement, complement is the same as A. Another property, A is a subset of B if and only if U except B is a subset of U except A. Let me draw the Venn diagram. So you have A, which is a subset of B. And then the whole thing is contained in a universal set U. Okay. So if A is a subset of B, then what about the complement? So you get the B complement. So B complement is here. So anything that is outside B. And then on the other hand, A complement is anything outside A. So it also includes, but it also includes all that is outside B. But it's actually bigger than that, right? And B complement is contained in A complement. So we can see here that B complement is contained in A complement. Okay, let's show that. It's actually easy to show. What does it mean that A is a subset of B? Of course, by definition, that means that for every X that is in the first set, then that X must also be in the second set. Now, this is a P then Q statement. Again, by tautological equivalence, this is the same as if X is not in B, that's the contrapositive, then X is not in A. That's the contrapositive statement. Well, if X is not in B, then it must be in the complement, right? So that means that X is in the complement. If it's not in B, then it's in the complement. Similarly, if it's not in A, then it's in the complement. So that means that the B complement is a subset of the A complement. Okay? So at this point, we were able to describe the properties of complement, the relative complement, and the absolute complement. Now, what if the operation involves the other operation, union, and intersection? So, what is the rule when those three operations are involved? Okay. So, this theorem, I will call trifecta of set operations. I'm calling it trifecta because this includes all three operations. So the theorem is as follow. You have A intersection B, which is this one. You have A except B. So A except B is anything in A. So this one. So looking at the set, we can easily or intuitively see na yung A intersection B, right? Together with A except B, those two actually forms the set A. Right? So we have the following theorem. So A intersection B, A except B together form set A. Okay. Let's prove that. So there are two statements to prove. First, that these two sets are disjoint, right? These two sets, this one and the intersection. So we need to show that they are disjoint. And secondly, we need to show that their union is A itself. Okay. So first, let's show that they are disjoint. Now, to show that they are disjoint, all we need to do is to show that their intersection is empty or that they contain no common element. So let's see. Now, for every x, what does it mean that x is in A intersection B? Well, that simply means that by definition, x is in A and x is in B. On the other hand, what does it mean for x to be in A except B? Well, by definition also of the complement, that means that x is in A and x is not in B. By simplification, this means of course that x is in B and this means that x is not in B. So now we have two contradicting statements. For x to be in the intersection, x must be in B, and for x to be in the complement, x is not in B. So if we combine those two statements, right? If x is in A intersection B and x is in A except B, then we will have the statements x is in B and x is not in B. But we know that these statements means that x is in the empty set. So that means the intersection of these two, so A intersection B, and A except B, if you get the intersection, the result is empty. Okay. So we're good with this joint. Now, how do we show equality? As always, whenever we want to show equality, all we need to do is to show that the left-hand side is the same as the right-hand side. Okay. So let's start with the statement A. Now, for every x, what does it mean for x to be A? Well, we can nothing much. There's nothing much to say. So now we need to figure out how to introduce B in the statement. Now, we can introduce this statement x is in B or x is not in B. Those are two statements. Pero we know that this statement is tautologically true. This is a tautology, right? If you have P or not P, this is always true. That's tautology. P or not P. This is equivalent to true. And that's a true statement. P or not P. Either umuulan o hindi umuulan. So, laging totoo yung statement na yon. It is always true that it is rainy or it is not rainy. It is summer or it is not summer. It is hot or it is not hot. It is cold or it is not cold. Okay. So, since that's a tautology, so by conjunction, you can include that to this statement. Diba? P, meron kang P, tapos meron kang true statement, therefore, P and T. Again, these are just logical statements, ha? So, dapat, we are clear with this one. So, if we have x is in A and quantity x is in B or x is not in B, then by distributive law in logic, so that means we have x is in A and x is not in B, or x is in A and x is not in B. Again, that's distributive law. That's why it's very important that you know your laws of distributive. You know all your laws in logic. The laws, the property, and the rule of inference. But as you can see, this statement is actually equivalent to the first compound statement means x is in A intersection B. And the second statement means x is in A except B. So the first one is the definition of intersection and the second one is the definition of complement. So meaning we have x is in A intersection B union A except B. But that's actually what we want to show. We started with the fact that x is in A and then we end up with this set. So therefore, we can say that the set A is equal to A intersection B union A except B. And that's done. So now let's show the De Morgan's law in set. This is actually equivalent to De Morgan's law in logic. Again, to review De Morgan's law in logic, not quantity P or Q is equivalent to not P and not Q. On the other hand, not P and Q is equivalent to not P or not Q. This is the De Morgan's law for logic. That's actually equivalent to these two laws here. So in set, we have the counterpart of De Morgan's law. So the union is equivalent to or, and the intersection is equivalent to and. So this is or and this is and here. So I will prove the first one and I will leave the second one as an exercise. Again, always do the exercises to reinforce the lesson learned here. So, as always, to show set equality, we will show that every element of the first set is in the second set and vice versa. So, what does it mean for an object X to be in A except B union C? Well, applying the definition of complement, so we have X is in A and X is not in B union C. So that's definition of complement. Now, we cannot use the definition of union yet because we do not have a definition for X not in. The definition requires X is in. So first, we remove the negation. So let me copy X is in A. So it is not true that X is in B union C. So that's negation. So now you can apply the definition of union. So let me copy again. X is in A. And it is not true that X is in B or X is in C. So that's union. Since the expression here is P or Q, we can now use De Morgan's law. So we have X is in A and so X is negating the first statement, then and become or, and then negating the second statement. Now, since these are all end statement, that means each of them are true. Again, this is De Morgan, by the way. So it is true that X is in A, X is not in B, and X is not in C. So since all of them are true, I can add by idempotent property X is in A in the statement. So I will include X is in A in the statement. So I have X is in A and X is in A. So that I have two X's in A. So why do I need two X's in A? Because what we want to show eventually, remember, is that we have A except B and A except C. So you need two A's in your statement. So by idempotent property, I can include another X's in A. Right? Okay, so after including X's in A, I will now use commutativity. Of course, first I need to remove the grouping symbol and then to reassociate X's in A and X's in B and then commute them. So by application of associativity and commutativity in that order, I have X's in A and X is not in B. And X is in A and X is not in C. So this becomes it's in A but not in B. So that's A except B. On the other hand, we also have X is in A but not in C. So that's X except C. So again, this statement here is from idempotent property. And then this statement here is from associativity and commutativity. So associative and commutative. And then this statement here is definition of complement. But since you have X and X, so you have X is in A except B, intersection A except C. But that's exactly what we want to show, that this set here is equal to this set here. So therefore, the first set, which is A except B union C, is actually equal to A except B intersection A except C. Again, the second one will be left as an exercise. To summarize, we discuss here three operations. So we have the union, so A union B, to be the set containing all element X such that X is in A or X is in B. So that gives us the union. Now, A intersection B is the set containing all X such that X is in A and X is in B. That's the intersection. And lastly, the third operation, A except B is the set of all X in B, in A rather, but not in B. That's the complement. Now, two important theorem that are extended, theorem from logic that are extended here in sets are distributive law and De Morgan's law. Of course, the other properties are equally important. We just have to make a distinction between distributive law since they are popular and commonly used property in logic. So the distributive law in logic has equivalent distributive law in set. So that means if you have A intersection B union C, you can distribute intersection in union. So that's A intersection B and A intersection C. So that's distributing intersection in union. You can also distribute union. So A union B intersection C is the same as A union B. So distribute union A union C in the intersection. Similarly, we have the De Morgan's law. So the De Morgan's theorem in logic also has an equivalent De Morgan's law in set. So A except B union C is equal to, this is actually similar to distributive law, but instead of keeping the operation, ang ginagawa natin, we are negating the operation. So A except B, the first set, so distribute A except C. And then instead of union now, we're getting the intersection. So De Morgan's is negating the operation. The end becomes the or becomes the end. Similarly, A except B intersection C is like distributing the set A except B. So we're distributing the complement A complement C. And then we're getting, instead of intersection, this time we're getting the union. Okay, so that's conclude our discussion of elementary set operations.